So the idea starts with a circle. If we take this circle right here, it has a center at the origin and a radius of 1. Now, if we think of any point on the circle, and we'll start with a point in quadrant 1. If I take this point right here in quadrant 1, and I draw a line straight down and straight across, does it make sense that the horizontal part is the same as your x-coordinate and the vertical part is the same as your y-coordinate? The hypotenuse happens to be 1 because that's the radius of your circle. If you're thinking of it that way, we can now consider points along this circle. Instead of thinking of them as their x and y coordinate, we could also describe any point on that circle if we thought about the angle in standard position. So there's an angle in standard position, and what kind of triangle did we make? We made a right angle triangle. So we can use SOHCAHTOA, sine, cos, and tan to explain some stuff. First of all, if we look at cos of theta, well, you know that cos of theta is the adjacent over the hypotenuse. So if we look, well, what's the adjacent side? It's x. What's my hypotenuse? It's 1. Oh, that's just x. And if you look at sine of theta, the similar thing happens. It's y over 1, which is just y. And tan of theta is opposite over adjacent. Well, in this case, it would be y over x. Now, this doesn't seem like very much, but this is the beginning of some major big ideas. First of all, instead of calling this point x comma y, we can now call this point, well, what's x equal to? It's the same as cos of the angle. So this point is cos of theta, comma, sine of theta. And so the first big idea, and we'll list them afterwards, the first big idea that we're going to run into is that any point on the unit circle, and that's what this circle is called because it has a radius of 1 and a center at 0, 0. That's called your unit circle. Any point on the unit circle, instead of describing it as x comma y, you can now just take the angle and describe it as cos theta comma sine theta. Now, we drew a triangle in quadrant 1. How does that connect? Maybe that only makes sense in quadrant 1. But if we chose a point in quadrant 2 or quadrant 3 or quadrant 4, and I'll choose one first in quadrant 2. If I choose this point in quadrant 2, well, if I drew a triangle, that would make that triangle. Does it still work if this is my new angle theta? Yes, because of what you've already learned about reference angles. If that's my angle theta, it makes a triangle, and there's my reference angle. And now I still have the opposite side here and the adjacent side that make that triangle. They still make an x and a y. Cos theta and sine theta still are x and y. But now all of a sudden, when I think of a point in this quadrant, can you see that the x-coordinate is going to be negative and your y-coordinate is going to be positive? And that fits with your cast rule. What do you know about cos and sine in quadrant 2? Sine is positive. Well, it's your y-coordinate. It still is positive. Cos is negative. Well, now it's your x-coordinate, and it will be negative. So this also explains your cast rule a little bit better than before. So there is big idea number 1. If you want to, at the bottom of page 470, So that's our first big idea, that all points on the unit circle are cos theta, comma sine theta. Well, as long as you have a radius of 1, that makes your unit circle. Now going back, question mark, there we go. The equation of a circle, and it used to be that equations of circles were taught more formally, but they're not in high school anymore. But I'll tell you that the equation of a circle, in this case the unit circle, is x squared plus y squared equals 1. But since every point x really represents cos and every point y really represents sine, we can rewrite this equation. Instead of x, I can write cos all squared plus sine all squared equals 1. And this is the very first formula on your formula sheet. Except generally, for whatever reason, they write sine first instead of cos. It really doesn't matter. And just something new for notation, mathematicians, they're inherently lazy. Well, not lazy, but they like to do things efficiently. So like, for example, we did coterminal angles. They're like, I could write them all out infinitely. That wouldn't be very efficient. Or I could think of a shorter way to write it out. And they really like writing things shorter. So you learn like the fancy z is all integers and the fancy r is all real numbers. And they've got all these symbols to go along. Well, mathematicians don't like writing brackets. So they're like, I want to get rid of the brackets. But the problem is if I get rid of the brackets, you won't know if I'm supposed to square the whole thing or just square the angle. So the notation that they came up with is if I want to square all of this, I put the squared in between sine and the angle. And I put the squared in between cos and the angle. If I put the squared after, it would mean just the angle is squared, not the whole thing. Equals to 1. You remember last year you had to memorize certain values? Like sine of 30 degrees was a half, and cos of 60 degrees was a half, and tan of 60 degrees was root 3. Maybe you have some of them still memorized. Maybe you've forgotten them well. We have to rememorize them again this year. So I'm going to get you to do some mental math. Okay? I'm going to pick one with square roots. Sine of 60 degrees. Okay? I'd like you to have sine of 60 degrees in your head. Got that number? I'd like you to square it. Keep that off to the side. I'd like you to take cos of 60 degrees, put it in your head. I'd like you to square that number. Keep those two numbers off to the side. Now take both of those numbers and add them up. What do you get? 1. Good. Some very good mental math people here. Wow, impressive. I'm going to give you a tougher angle. Okay? Something that you didn't memorize last year, 23 degrees. I'd like you to do sine of 23 degrees in your head. Keep about 50 or 60 decimal places. Okay, good. Now square that. Okay, good. Keep that number off to the side. Now I'd like you to do cos of 23 degrees. This time keep about 75 decimal places. Okay, now square that. Take both those numbers, add them up. It's equal to 1. Wow, you guys really have good mental math skills. In fact, this is big idea number 2. It doesn't matter what angle we have, sine of any angle squared plus cos of any angle squared is equal to 1. So if I put 23 degrees in there, and like I got you to pretend I should have checked halfway in between. Can you give me those numbers? But I didn't. If you square them and add them together, you will always get 1, even though you can't do sine of 23 in your head. We just did. We just proved it with this little diagram and the definition of the equation of the unit circle is x squared plus y squared is 1. And we know that every x is cos of theta. And we know that every y is sine of theta. And so we're able to say this is always true.
Oh, I see. A squared plus B squared equals C squared.
And all it is a squared plus b squared equals c squared. And that's the equation of your circle. Can you see that your circle is just the Pythagorean theorem? A squared plus b squared equals c squared. But your hypotenuse is always 1. And so you get this equation. Pretty cool. The last big idea that we're going to have from this little circle and just drawing a triangle is looking at tan. Well, tan of theta is y divided by x. But if y is the same as sine and x is the same as cos, the third big idea that we're going to learn is that tan of theta is always sine of theta divided by cos of theta. You can take out your calculator to check. You can go tan of 23 degrees, push enter. Then again you can do, well, what's sine of 23 degrees divided by cos of 23 and push enter? You get exactly the same answer. And it's always true as long as the angles stay the same. Notice it's theta, theta, theta. We're not changing the angles. You can't put 23 here, 40 there, and 10 there. Then it doesn't work. But if all the angles are the same, it will work every single time. Now, these big ideas, we use them so much that by the end of the year, by the end of this semester, you will feel like, oh, that's common sense. There's certain things in math that you think are common sense right now, but they weren't for you 3 or 4 years ago. A squared plus b squared equals c squared. Do you feel like everybody that's taken math should know that? Like that's just something people know, right? But it wasn't, when you first learned it, it was like, oh, this is weird, this is new. I don't know what they're talking about, right? SOHCAHTOA, if that's how you remember it. Does anybody rearrange it? Toa Kaso? Anybody do it in different order? No? No. But you could, right? And we're going to learn in this unit, we're going to learn the reciprocal functions for sine, cos, and tan. So you're going to learn about cosecant and secant and cotangent. But at the end of the year, these ideas you're going to feel are common sense. That you've just known them your whole life, even though you just learned them today as your 3 big ideas.